please start. So next talk is by Chang-Wang Park on most probable behavior of dark energy, EoS, indicates a thawing quintessence field. Okay, it's a very long title, so.
Okay, good morning. It's my great pleasure to come back to Bengaluru, India again. And I'd like to thank Tarun, Subir, and Probable, and all the organizers for inviting me here. I checked my record and I found that I was in Bengaluru 10 years ago, almost 10 years ago. And at that time, I talked about the same thing. But at that time, I explained the method, and today I'm going to report the result. So there will be a big difference between 10 years ago and now. Okay, so this is one-page summary of my talk, and we measured the average value of dark energy equation of state parameter W, and then we measured the first time derivative of W as well. So about 3 years ago, we reported that the average W from G equals 0 to 0.7 is about minus 0.9. And we managed to have very small error bars, and it is 4.2 sigma away from minus 1. Therefore, we ruled out the flat lambda CDM model at 4.2 sigma level. And this year, we measured the first time derivative of W under CPL parameterization of W, and we measured WA to be basically consistent with 0, but slightly negative. And that means we do not find strongly evolving dark energy equation of state, and also the most probable behavior of W of G indicates there's no phantom divide crossing, at least before G equals 0.7. So I'll describe more in details. Before I start to explain what we have done, I'd like to emphasize need for small scale, the statistics on small scale to constrain cosmology to great accuracy. And the reason is we are running out of statistics from these galaxy clustering studies, because even so, if you use BAO to measure, to constrain cosmology, the number of information you get will not be very much. So even if you obtain all the redshift of galaxies within the visible part of the universe, namely, suppose you observe all the galaxies out to the redshift 10, and then this moving distance out to redshift 10 is about 6,000 megaparsec, 6 gigaparsec, and therefore, number of independent elements within this visible part of the universe, galaxy world, is only about 10 to the 5. But if you use, for example, the Alko-Patinsky test, like the one I'm using, you can use information on 10 megaparsec scale, and basically the effective size of data is 1,000 times larger. So that makes a lot of difference. And of course, every statistics should be corrected for any potential nonlinear or non-Gaussian effect. And as we go to 10 megaparsec scale, you have to worry about the small scale nonlinear astrophysics. So you have to be very careful in choosing this kind of statistics. And the statistics we are using is the large scale structure topology, which is very insensitive to gravitational evolution and biasing, and also the redshift space two-point correlation function, which I'm going to explain today. And both statistics can be used at 10 megaparsec scale, which makes your data effectively very large. Okay, so let me explain how it works. So suppose we are living in a flat lambda CDM universe with omega lambda 0.74 and omega matter 0.26 and W equal -1, of course. And you are observing the galaxies at the four corners of this blue square, and you are sitting here. And there are 4 scales, and all you get is the redshift of these galaxies sitting at the corner. And you adapt the cosmology to convert this redshift to co-moving distance. And suppose you chose the wrong cosmology, namely, in this case, you overestimate omega matter and calculate the co-moving distance, and then you underestimate the distance, so this scale will appear closer to you, but also it's a bit squashed. If you underestimate omega matter, then the expansion of the universe is overestimated, and your apparent distance to this galaxy will be overestimated. So this scale will be showing up at larger distance, but also it's going to be stretched. So depending on the cosmology you choose, the shape of this object will be distorted. And this stretch factor is like this, as a function of redshift. In this case, you underestimate like this, and in this case, you overestimate this. And therefore, if you use some object for which you know the shape, you can constrain the cosmological parameters that govern the expansion history of the universe. So this is basically how we are able to constrain the dark energy equation state parameter. Okay, so I'm repeating the same thing, but in a different way. Suppose you have galaxy data, so you have angular position and redshift. You adopt a cosmology, namely R of Z relation, to convert redshift to co-moving distance, and now you have 3-dimensional position of each galaxy. And therefore, you can make a map like this, and then you divide your sample into few non-overlapping redshift shells, and then calculate the correlation function in the 2-dimensional space along and across the line of sight, and then you compare the shape in one redshift bin to another, okay? And then you have to take care of the expected evolution of this shape, okay? Which can be derived from a set of cosmological simulations which takes into account the gravitational evolution and galaxy bias. And then you check if the shape of correlation function evolves given the cosmology you adopted. So you try many different cosmological models and choose the model which minimize the evolution. And that's your best fit cosmology.
What do peculiar velocities fit in here? Finger of God, etc.
So the correlation function we use is the correlation function in redshift space. Okay, so we don't need to correct for the peculiar velocity. So there is slight difference compared to original Akopachitsky test. In original Akopachitsky test, one needs to know the shape. And in each redshift, you compare this known shape with the shape you measured. But in our case, we don't need to know the shape. We just compare the shape in one redshift bin to the shape in other redshift bin. So you only care for this difference. So you don't need to know the size or shape, and only the shape conservation is needed in this case. This makes our method independent of many other cosmological parameters, other than those that affects the expansion history. Okay, so the standard shape we choose is normalized redshift space 2-point correlation function in this study. And let me try to explain why this is good. So here, this is a 2-point correlation function calculated from embodied simulation at redshift 0, 0.15, and 0.5. Okay? And this is the difference between these two correlation functions and this correlation function. Okay? And you can see in this redshift space distorted correlation function, the amount of distortion in one point in this to another is of order of 1. Okay? So there's a lot of distortion, but the difference, the expected evolution of this shape is of order of 0.01. Okay? So it's 100 times smaller, and that is what you need to correct using simulations. And the So the correction can be made very accurately, and the uncertainty in the correction is another order of magnitude smaller. We use Sloan redshift survey data, which is broken into 6 redshift bins. The bright galaxy, so I'm using DESI data right now, so I'm a bit confused in names. This is the main galaxy sample, and the LOSI and CMAS. Okay? So we have 6 redshift bins. We decided not to use this EoS, which has too noisy. The correlation function we measured in each redshift bin looks like this. This is the two-dimensional correlation function measured from the first redshift bin, which is the main galaxy sample. And this is from LOSI, and there are 3 data from CMAS. And if we overplot all of them, they look like this. So in this calculation, we adopted this lambda CDM. Okay? And you can see the shape of correlation functions all overlapping with each other. So by eye, you cannot see any difference, which means lambda CDM is already very good. Okay? So, but it turned out that it can be still improved, and there's other model which is better than this, better than lambda CDM. So this is the result from comparing the shape of correlation function in 6 different redshift bins. And the two, so this is the average dark energy equation of state parameter, W, and this is the omega matter, total matter density. And these two are the ones that affect the expansion history in this cosmologies. And in omega matter and W space, I'm also plotting other constraints. And our concern is this pink one, and BAO is up there. This is SDSS BAO, and this is supernova, and this is Planck CMB. And if you see only these low redshift probes, then there is one spot that overlaps with each other. So there is 1 sigma regions are all overlapping at one spot, but there is no good overlapping with CMB. So if we combine only these low redshift probes without combining CMB, we get this constraint. And we found that W equal minus 0.9, and it's 4.2 sigma away from -1. And therefore, at this 4.2 sigma level, we can rule out lambda CDM. Sorry, it's not 5 sigma, but it's close to 5 sigma. Okay, so this was more than 2.5 years ago. Okay, it's a combination with BAO, basically. So, right, so yeah, this orange one. So the supernova didn't help much because it's basically parallel to our constraint, but BAO basically shrank our error bar a little bit. Okay, so they helped because it has some angle to us. I'll tell you later. Okay, that's critical point of my whole talk. Okay, I'm not in that position to answer. Okay, it's CMB people to answer. So in only 2023, still there was more than 1 year before DESI first year paper, and nobody was talking about deviation from lambda at the time. So it was not very well accepted at the time, but I show you it was confirmed by DESI itself. The DESI paper submitted this year, and you can see this is not DESI only. This is CMB plus DESI plus supernova, in this case uniously. Okay? And there's only one significant, one data point that is significantly away from -1, and that's the first bin. So these are not independent measurement. It's just the bin W measurement in different binning scheme, and others are not very well measured, but this one is clearly suggesting that W is away from -1, actually greater than -1. And the value is actually almost exactly the same as what we measured before. Okay, so we basically, she confirmed our measurement. Okay, so this year we extended our analysis to measure the time derivative, average time derivative of W. So we constrain, now we have two more parameters. So including omega matter, we have 3 pre-parameters to constrain. So therefore, the constraining power drops a little bit, but still our AP test is so powerful that we can still talk about very interesting constraint on W without combining with CMB. And WA measured here is basically minus 0.17 plus minus 0.4, and therefore is basically consistent with 0. Okay. And this is a supernova. And it's a bit difficult to see, but behind this contour, there's a blue contour. And this blue contour is the joint PDF of supernova and BAO-BAO. Okay? And if we combine this blue contour with this magenta contour, which is from AP test, we get this orange contour. So this orange contour is the joint constraint from SDSS AP and dash BAO and supernova continuum plus. Okay, so this is this, and it compares with the report in the DASH paper, DASH 3-year paper. This is from Planck CMB and DASH BAO and supernova 1A, and there are three different kinds of supernovae here. And if you look at blue or green here, and they can be able to say, basically this area is more than 3 sigma away from WA equals 0. So the main conclusion of this report is that there is a evolution in W, strong evolution in W. But in our case, basically statistically consistent with 0, but the most probable W seems to be maybe much slowly evolving. You may ask what's the difference between this and this, and main difference is the inclusion of CMB data. Okay, and let me show how this happened. Oh, well, in another way, so this is the result I just showed you, and if I plot this in terms of W of Z as a function of Z, and this is basically what we predict. So this is the most probable ratio evolution of W, whereas this green band is the most probable evolution of W reported by DASH paper. And there is fundamental difference. Okay, so here you see there is a phantom divide crossing at ratio 0.4, whereas we do not measure any phantom divide crossing out to G equal 0.7. Okay, and therefore this suggests that the dark energy may be Thawing quintessence, whereas here you have to think of some other models. Okay. But what is important is if you don't include AP test and also don't include CMB and only combine DASH and supernova, this is again consistent with our result without combining our result. So this is still, WA is still very small, and it suggests no crossing. So it's only when CMB is added, you get this phantom divide crossing at G equal 4. So you may wonder what's going on, and here is an explanation. So this is the constraint on W0 and WA from dash BAO only. Okay? And they put this prior to WA to be greater than -3. If they don't apply the lower limit of -3, I don't know how far it will go. Okay? And the 1 sigma error bar and 2 sigma error bar may change as well. But anyway, accepting this prior, you can combine BAO data with supernova, or another supernova, to get this. And you can see this combination tells you WA, maybe most probable WA is slightly negative, but cannot have between WA equals 0 and this most probable one. So basically, these are consistent with WA equals 0. Now, let's see what happens if we add CMB. So this is the constraint from CMB only. So it has very weak constraint on these W parameters. And it's almost parallel to this. So if you combine this one and BAO, the joint PDF is appearing over here. And you get very tight, very narrow contour. And it appears to be statistically very significant, but that is because they are not overlapping much. So if they disagree more, you may get even tighter constraint. Okay, so I overplotted this one with this. So this is the joint constraint from this and this. And phantom crossing is due to the shift and slope of CMB. What I mean is CMB is shifted to the left, it's at the bottom. So whenever you combine some constraint with CMB constraint, and your value of WA is going to be more negative. So that's what's happening. So even our constraint is this one, this pink one. So this is the one I showed. This is my main result. But if I also combine my result with CMB, the joint constraint will be this. So WA will move from minus 0.15 to minus 0.62, and I'm going to get phantom crossing. So you can see how big CMB constraint is, but how big the impact of CMB combining with CMB. Okay? So because your physics completely changes by combining CMB data, you got to be very careful. You cannot just rely on statistics. You should check the physics you're finding. Okay, so let me conclude. 2.5 years ago, we published our result on average W to be 0.9. And this, it is this point. This red point is the one we got 3 years ago. Okay? And this curve is what we got this year. And we see there's no phantom divide crossing up to 0.7. And the kind of dark energy you can easily think of is this Thawing quintessence field. This is my conclusion. Thank you.